Hello, my friends. In this video, we are going to calculate the torque and maximum torque of the induction motor. In the last video, we have already established the model for induction motor. The model itself is basically very similar to the model for the transformer. And in the transformer, we have the primary and secondary. And in induction motor, we use the primary to model the stator, and we use the secondary to model the rotor. And from here, we end up with the parasitic for the stator. And because the stator itself is basically a stationary device with an array of electromagnets. So it's exactly the same as transformer with the winding nodes, winding impedance, and the core loss and the core impedance. And the rotor itself is modeled as a secondary of the transformer. But there's a difference between the rotor and the secondary of the transformer. The difference is in the resistance. And uh, in the secondary of the transformer is not motional. It's not something that can move. But in the induction motor, uh, is rotating. The rotor is rotating, and is the rotation of the rotor uh, is going to involve the formula for the slip. Okay, so that's why we end up with the circuits like this. And now, and we also develop some formula for the power loss and the power input. The power input is going to be uh, V times the conjugate of I uh, and multiplied by 3 because this circuit is only the circuit for one phase of the induction motor. And the core loss is the same. Uh, we can use the voltage here, right? B times the absolute of the voltage divided by the core resistance. Then we will end up with the core loss. But the power for the air gap is the power that belongs to the uh, to the power uh, to the power consumed on the right side of this red line. In the right side of this red line, we only have the resistance term here, which is responsible for power consumption. So that's why uh, the air gap power, which is the power for the rotor, is 3 times I magnitude, I2 magnitude, times RT, RT dash divided by S. Uh, we use the current and the resistance here to calculate the power belonging to the rotor. And now we can also evaluate the power based on the relations in the input output here. Yeah. First of all, the power that goes into the motor is P in. And at this point, the power is um, should be the input power minus the power for the winding loss and minus the power for the core loss. So we can say this, right? P in here. P in is given by this equation minus the core loss uh, and the winding loss. And so these loss, after subtracting these loss, then the power for each element is the AirGap power. Uh, Now we are going to continue. We know that according to here, the converted power is the AirGap power times bracket 1 minus S. So let's write down here. And we need to free up some space now. Let's remove this. Let's highlight this in here. So this one is going to to consume the winding loss at the stationary. And this one, the core loss due to the iron loss. And this one, air gap. So we don't need to write so much, right? We immediately know everything about the circuit. And we also know that the core loss, the converter power, I mean the power for the motion. Let's for the time being, let's have some assumption first. Just assume let's ignore the friction. Then the converter power is the power subtract all the electrical loss. So in this case, P convert is going to be P AG 1 minus S. Now, according to what we have derived down here. And now the converter power, if we ignore friction, and this converter power will be used for mechanical action. And the mechanical action include the torque. As we know, the power is given by the angular torque times omega. Omega, I mean the speed, the angular speed for the rotor. And then P AG times 1 over S. But then do not forget that The torque times the angular velocity. The angular velocity is given by 2 pi and then nr divided by 60. But this guy can be, according to what we have done, is actually the rotating magnetic, the speed of the rotating magnetic field minus 1s. So essentially, you have the little expression here for the synchronous speed. So essentially, right, you can also do this. So if it is the case, then the torque is going to be, yeah, we have the 1 over 1 minus s in both sides of the equation. So we can actually cancel this term, yeah? And then the torque here is going to be dAg divided by uh, 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 omega s, the synchronous speed, the speed for the rotating magnetic field. So this is the torque. And from here, we also know that the the air gap power is dependent on the slip, and the rotating angular velocity of the magnetic field is dependent on the frequency only. Uh, is dependent on the frequency and the number of poles in the motor. So now, what we can see here is, right, if the for this guy there is no maximum or minimum, the frequency is fixed. The the number of poles is also fixed. The only thing that is variable is the air gap power. The air gap power depends on the slip. So there must be a slip that gives rise the maximum air gap power. But down here, right, let's agree for the fact that the maximum torque is going to happen when the air gap power is maximum. So this is a very important conclusion of the exercise so far. And I don't have enough space. And uh, like what I said before, right? The torque sleep characteristic is like this. And we have a local minima here. And this one is so-called pull up torque. And this one is so-called pull down. Sorry, pull out. And And here the sleep is 0. Sorry, the sleep is 1. And in here the sleep is 0. And we also have a startup torque here. So this is the torque sleep characteristic. And uh, right now we already established the relations for the torque. And what we don't get is the relations for the maximum torque. And before going forward, right, let's fix this problem first. The torque, right? The torque according to here is the air gap power um, minus the divided by the synchronous power. The synchronous angular velocity. Sorry. Now let's move on. Yeah, T here according to here is equals to PAG, which is the air gap power, divided by uh, the synchronous speed of the rotating magnetic field. And we don't need that much space to explain everything. And this air gap power is the input power minus the copper loss and core loss divided by omega s, which stands for the angular velocity of the rotating magnetic field. So this is the expression for the torque. And now, as an engineer, we also want to maximize the torque, and that's why we are here. And remember, we have this circuit here, and this circuit can be converted into a Tetris equivalent. So for the time being, right, we have already got the red line here, and let's convert on the uh, everything on the left of the red line into a Tetris equivalent. So what I'm saying here, right, we convert this circuit into this one. VTH, and then the reactant, the impedance of Teflon. So we have RTH and XTH here. So this is what we have on the left of the red line. And on the right side of the red line, we have JX2, yeah, and then the resistance. The referred resistance of the rotor divided by S, where S stands for the slip. So this is the circuit we can get after the conversion process from this circuit to Teflon. And if you do it carefully, you will find that the Teflon resistance here is actually given by um, the view part Is it good to, we don't need that, right? We just write down the whole thing. The tapering resistance plus the tapering impedance. Oh. Is we have to assume the voltage to be zero. So in other words, right, we have this pair and this pair. So the tapering impedance is actually uh, uh, this guy parallel with RLC and then JXM. So this is the tapering impedance. And now the tapering voltage is we can use the voltage divider model to model it. Right? So it's going to be RC. We put a J here as well. Okay, uh, and then the bottom one plus, and then times the voltage one. So this is the tapering voltage and tapering impedance. And with this, right, we end up with this circuit. Now the point is, right, how do we know the? We have already got these relations for the torque, and from here, the angular velocity of the rotating magnetic field uh, is not going to change. Is independent of the slip. So in this case, the only thing that is variable is the air gap power. If the air gap power is maximum, then we know that the torque is going to be maximum as well. So this is a very important conclusion based on what we have observed here. The idea is we want the maximum power to be transmit, to be transferred into this resistance, and this resistance is the only one that is responsible for the air gap power. So to ensure maximum transfer of power, we need to use the maximum power transfer theory. The, yeah, according to here, well, for the time being, I'm going to remove these two lines. Include only these two lines for the time being. Okay. Uh, we have already got this right. We know that the maximum power is going to end up with the maximum torque according to this equation, and the air gap power is uh, and is this much, right? And it can be calculated according to the current here. And for now, uh, the current here is I2 dash, which is the referred current from the rotor. So let's write down here. And in order to maximize the power, we need to come up with some figure. And for the time being, right, we are not able to to modify the reactant of the rotor, but instead we can change the slip in a way to change the resistance of the referred resistance of the rotor. So let's do it. So now uh, we are going to maximize the power transfer into this guy. And the impedance that we are dealing with is that much. So we are not going to rely on this line anymore. So this is the circuit. And for the AirGap power to be maximum, for PAG to be maximum, the the R2, the resistance value here has to be equal to the absolute value uh, of the impedance here. So it's going to be R J XTH and plus X2. So this is the value of the resistance for the rotor. And in here we can highlight the fact that this is the slip that is going to give out the maximum torque. So if you want to calculate the slip that will end up with maximum torque, then what we can do is S maximum is going to be R TH plus J XTH plus X2 divided by R2 dash. So this is the slip that will end you up with the maximum torque. So this is the mini conclusion for this chapter. If you have any questions, feel free to leave your questions through the comments box underneath the video. Thank you very much for your support.